In the last video, we spoke about this particular exercise about under what circumstances can the method call be valid. And you have to consider the argument static type and also the parameter static type. And also you got to consider the variable substitution that will be done implicitly by call by value, right? That's the essence for the earlier video. I assume you already got it. Otherwise, you have to go back and review it. All right, let's now talk about another interesting exercise, okay? So this exercise set contains 4 of them. So I would suggest actually you study the slides yourself, and for me, rather than reading off the slides, I'm gonna show to you the ideas about how the 4 exercises are supposed to mean to you. All right, let's now take a look. I put all the 4 exercises in a single page over here, 1, 2, 3, and 4 over here. Let me talk about all the points I think that should be conveyed to you one by one. Okay, hey, let's recall. From the student management system class, this is the method declaration. So we have a mutator at rs. The static type for the parameter rs is the resident students, right? Let me just highlight it quickly for you. So rs is the parameter, okay? And of course, we may have the various arguments of different static types. That's what we'll look at. Okay, and for now, don't worry about this line just yet. Okay, for now, let's now take a look at each of the example over here, 1, 2, 3, and 4. Let's now consider their first line just to do some warm up. Right, the first line all declares some static type of variable s over here, and this static type is NRS, right? Oh, sorry. This one is declaring some variable NRS of different static type. I want you to judge first whether or not the first line over here odd, valid or not. The substitution. All right, you can pause the video and think about it. All right, assuming that you thought about it, let's see the first line in the first example. Here, the dynamic type students is a descendant class of the static type over here. So that's why it would be valid. You can see students is a descending class of itself. So that's fine. Similarly, let's look at this one. Non-resident students over here in the hierarchy is a descending class of students, the static type. So that's also fine, right? So the other two, you can argue the same way. So all these substitutions are simply just valid, okay? So I'll put a check mark on the substitution here. So this is okay. So this is okay. This is okay. And this is also okay. All right. So far, nothing surprising. And of course, you can also look at the comments I put there about the static type and dynamic type, right? You can see the static type over here for all these 3 examples, static type is really the same. It's just that dynamic type is different. Meaning that when you do some upward or downward casting, you got to be careful whether or not you might run into Classcast exception. That's what we'll see. All right, let's now continue. And the third line for each of the example, we simply just create student management system instance, SMS. In this case, it's not so exciting to worry about the substitution because dynamic type and static type is simply just the same. And there's no hierarchy actually for student management system for the inheritance. So that's fine. So I think for line number 3, for each of the example, it's just to make sure we have some context object to invoke the add rs method. That's it. Okay, so now let's focus on the lines I'm going to highlight. Okay, let me highlight every one of them. Line number 4 over here. Line number 4 over here. Line number 4 over here. And also line number 4 over here. I already put the cross marks over here for each one of them already, telling you they are not valid. They are invalid. Can you please pause the video and tell me the detailed reason for why each one of them would not be valid when we try to make the method call? All right, pause the video and think about it. All right, assuming that you thought about it, and the answer should be really based on your study from the earlier video, right? Let me just take one example here. If you take a look at here, we are trying to say add rs. So we are calling this method over here. And then we are trying to use, let's say, s over here. That's the arguments. The argument is of type students over here. Okay, and call by value is going to make sure when you try to make this particular method call over here, right? Call by value. I'll just do the first one. You can do the rest yourself. Call by value is going to do RS is assigned to S, right? So when we do this particular substitution, whether or not it's valid is you're going to look at the static type for S, which is students. Okay, so the static type for S is students. The static type is declared as students over here, right? Let me just highlight it once more. Oh, let me just highlight it a little bit better. I don't want to cover the name. The static type is simply students. And what about the static type for the parameter? It is declared by definition as the resident students. The static type is resident students. So the question is, can students fulfill the expectation for resident students? The answer is cannot, because students is not a descendant class of resident students. So that's a detailed reason, right? So that's something you should feel very comfortable about writing down, right? I'm just mentioning that verbally, since I already wrote it down in the earlier parts for the inheritance lecture. You can look at them up if you got any question. All right. You can do the similar arguments about add RS and also add RS over here. One question for you. Let's say for this one here, right? This one specifically. Let me just visualize this one only. Let's say S. You can see what we have is we actually got students S pointing to some resident students objects, right? Over here, and what we have is a resident students objects, which of course by definition should have the premium rates attributes. I'll just RS for short. Okay, resident students. Of course, we got a premium rates PR attributes. Why can we not pass S over here to RS, which is also expecting a resident students? And indeed, this is a resident student objects. So why would it not compile? Right? So now we are going back to our relevant A+ challenge. The compiler can simply not infer that at this point S is really pointing to a resident students object. The compiler simply cannot. It's an undecidable problem. The only thing the compiler can do is to only look at a static type for S, which is only students, even though its dynamic type is resident student. But that's not relevant. It's not something the compiler can infer. So for argument S, it has a static type students. And for RS, its static type is resident students. Can students fulfill the expectation for resident students? The answer is it cannot. So that's why this also wouldn't compile. Be very careful. All right? It's something I want to also emphasize. And you can do a similar arguments for this one as well, right? When you want to do NRS over here, right? To see why it is invalid. All right, so that's the point I want to mention. Let's go to the next point. The next point is, given that the static type of S over here as the arguments cannot really fulfill the static type for the parameter resident students, why don't we try to do a cast? Okay, if we try to do a cast for each one of them, specifically this is the cast I want to do. Let me just highlight to you. Since the parameter is really expecting resident students, so why don't I try to cast the arguments to resident students? So that's what I'm doing here. Okay, so you can imagine that for each of the line number 4, I'm simply going to replace them by the following line. This one here. I say SMS, the context objects, at RS. I'm still calling the same method over here, but now I'm going to say S, rather than using S, which has been declared as student static type for each of the cases over here. And let's not talk about the fourth one. The fourth one is a little bit different. Okay, only talk about the 3 examples at first. So 1, 2, and 3. The static type is simply just students. If I try to cast them into resident students, number 1, does it compile? Well, given that their static type is actually students, right? You can see students over here, student over here, and also student over here. The static type is actually students. And I'm trying to cast them into resident students over here. So that's the cast type. Are we doing upward casting or downward casting? Well, apparently we're doing downward casting, which is valid for sure. Downward cast. Okay, it is valid for compilation because it's downward casting. Okay, but number 2 is, are we going to get Classcast exception? We want to answer for each one of them. are we going to get runtime exception, specifically Classcast exception? Runtime exception, right? There's always two questions you want to ask about any particular cast. Number one, whether or not it is valid to compile. Number two, whether or not it's going to run into runtime Classcast exception, right? It's something we also spoke about in detail earlier. Okay, let's now talk about each one of them, right? For example, for this one here, if we replace line number 4 here, if we replace this line over here by this line, first of all, we know that it's a downward casting, so it will compile. Are we going to run into Classcast exception? Yes or no? Okay, pause the video and think about it. All right. Let me, assuming that you thought about it, so let me just remind you, when should we get the Classcast exception, right? In this case, since we are casting S into something else, right? Classcast exception only if the dynamic type of S, in this case, it will be different between examples, which means we got to talk about case by case. It will be a Classcast exception if the dynamic type of S is not a descendant of the cast type. And in this case, we'll cast them into resident students over here. Resident students. All right, let's highlight this point, which is very important. If dynamic type of S is not a descendant of the cast type. Right, let's now talk about it. Right, the cast type is always resident students. Now, in the first case, the students is here. Is students a descendant class of resident students? Can the dynamic type students fulfill the expectation for resident students? The answer is no, it cannot. Right, so that's why there will be a Classcast exception for the first one. Okay, so for the first one, you can see this is for this exercise over here, this is for this exercise over here, and this is for this exercise over here, right? So for this, the first one, yes, there will be Classcast exception, again, because dynamic type for S is actually students, and you're trying to cast that into resident students. Again, you're trying to cast students into resident students, but students cannot really fulfill resident students' expectation. That's why it will not. There will be Classcast exception, even though it will compile. What about example number 2? When you try to cast non-resident students dynamic type into the cast type, which is resident students, can you do that? The answer is no, you cannot, because non-resident students is also not a descendant class of resident students. Okay, let's now write it down. Okay, so this one also, yes, we got Classcast exception because the dynamic type of this S object over here in this second exercise is non-resident students, is not a descendant of the cast type, which is resident students over here. Right? Again, that's very important for you to know that, right? Dynamic type of NRS, dynamic type NRS over here is not a descendant of the cast type RS, which is over here, right? Okay, let's now go on to the third exercise, right? For every one of them, you want to be very clear about why they compiles and also whether or not you will run into Classcast exception. The third one, hopefully you can see that you would not run into Classcast exception because dynamic type is over here. Can it fulfill the cast type? Indeed, they are the same. A class can definitely fulfill the expectation of itself. So the answer is, for this third exercise over here, there'll be no Classcast exception because dynamic type resident students can fulfill expectations of the cast type, which is resident students. right? Because a resident student is simply a resident student here is simply the descendant class of itself, which is happen to be the class type. All right, so that's about exercise number 1, number 2, number 3, right? Again, I'm trying to present in a different order, in a different way that's actually statically written on your slides. I'm just hoping to strengthen your understanding, but you should still go over the slides as well, which I also try to give you detailed explanation there. All right, final exercise number 4 over here before we end the current video. Okay, what about this guy over here? We talk about line number 1 should compile, and also line number 4 should not compile. We spoke about them already. So now, if I replace this line over here, NRS, I know that the parameter is really expecting resident students. So that's why I'm casting NRS into resident students. Are we going to get Classcast exception? Pause the video and think about it. Okay, assuming that you thought about it, the answer is it's actually not showing very good understanding when you even ask me, are we going to run into Classcast exception? Because this line may not even compile in the first place. You see what I mean? If the code doesn't even compile, how can you actually execute it at the runtime and get a chance to really run into Classcast exception? Okay, let's see what I mean. If you look at this, let's be careful again. Whether NRS over here, what's its static type? Static type is actually its NRS declared to be non-resident students, right? Non-resident student. Let me just draw the redraw the diagram here again. Students, and we got resident students, and also we got non-resident students, right? You can see here the static type is actually NRS. That's the static type for NRS, and we are trying to cast that into resident students, right? So what we're having is RS is the cast type, and the NRS over here is the static type. Okay, is that upward casting or downward casting? The answer is neither. Casting for NRS into its sibling is neither upward nor downward casting. So that's why this cast exception, this cast expression over here will not even compiles. Okay, that's why I was asking this. Would it compile? Unlike for exercise number 1, 2, and 3, right? For 1, 2, and 3, since all the static type are simply student, so you can that's why you can downcast to resident student. That's okay. But now the static type is actually NRS over here. You cannot cast that into RS. You cannot. Of course, you might be asking, can we just upward casting and then downward casting? That's another story. You can refer to the earlier exercise that we did last week. All right, let me write it down here. No, it doesn't compile. Okay, no, it doesn't compile because the RS over here, the cast type, is neither ancestor nor descendants of the static type, which is NRS. That's the detailed reason. Okay, so that's about the 4 exercises. Okay, let me just go back to the slides, but on the iPad I already explained to you in detail, just point by point, about what you should really know about these examples. But you can still go over number 1, number 2, number 3, and also number 4. Okay, and study this very carefully, and then we'll move on in the next video about a very important concept to conclude the topic about polymorphic parameters, which is called a polymorphic collection of students.